Okay, good morning, everyone. So my name is Siyoum. So today I'll share with you some insights on the topic of Edge AI from industrial applications perspective. I am from Signify, which is a lighting company. So the scope of my talk is some application areas where we think Edge AI could help us to address some challenges in the lighting industry. Yeah, so mainly from application point of view, we are not an AI company. So maybe to say a few words about Signify. So Signify is a global leader in lighting. It is, maybe you know it better with its former name. It's called Philips Lighting. So the company rebranded itself to Signify in 2018. We have products in the complete lighting spectrum, but some of our known brands are Philips Hue, Wiz, and Signify Interact. Maybe you already recognize some of those brands. About myself, so I've been working with Signify for the last 10 years. So my team develops firmware and control systems for wireless sensor nodes. These wireless sensor nodes are used in indoor lighting systems. So the sensor nodes are embedded into luminaires, which are in indoor lighting systems deployed in offices or schools or hospitals, industrial facilities. My background is, my academic background is in electrical engineering and embedded systems. Actually, I'm happy to see here today Professor Hein Corporal, who was my supervisor at TU Eindhoven. It was a nice coincidence. Okay, so Interact smart lighting system, what does it look like? So if you consider a typical, let's say, a 10 plus floor building, office building, typically there are thousands of lighting points. So even we have some projects where we have more than 10,000 luminaires in a single site. So these luminaires are equipped with drivers which have a wireless connectivity support for Zigbee and Bluetooth. And we organize these luminaires into Zigbee networks. So there are multiple Zigbee networks. Each Zigbee network can have up to 200 nodes. And optionally, each Zigbee network can have a wireless gateway. So then that wireless gateway provides cloud connectivity where using, let's say, a web app, users can have central monitoring and control to the Zigbee network. So besides that, each node also can have a point-to-point connection with a mobile app where users can have direct control of the lights. Yeah, so this is a typical IoT system, and then at the edge of this IoT system, we have these wireless sensor nodes. These are edge devices. So as I said, they have wireless connectivity support, mainly for Zigbee and Bluetooth, and next to that, they also have some sensing capability. Yeah, so typical sensors include motion sensor or ambient light sensor, temperature sensors, humidity sensors. They are all integrated into these tiny sensors. I think I have some samples over there. But, for example, this motion sensor, we use it to implement occupancy-based lighting, which is basically a key feature of smart lighting systems for energy savings. So another feature we also do is daylight-dependent regulation. So that means using a light sensor, we can measure the ambient light level, and then if there is sufficient natural light in the room, so we can adjust or dim the light level or even completely switch off. And then this helps in energy savings. So energy savings is one of the key use case of smart lighting systems. Beyond that, we also use data from a temperature sensor or from a humidity sensor to integrate it with the building HVAC system, so that we can also build an automated climate control. Yeah, so there are also more beyond lighting applications by using these wireless sensor nodes. So how do we implement those applications on these tiny edge devices? We implement our applications basically, typically using finite state machines. So there are multiple of them for different applications. So a typical finite state machine, it consists of states, transitions, events, guards, and actions. So when a certain event is triggered, so the state machine will check if all conditions are met. If conditions are met, then a set of actions will be executed, and the state machine will transit to a new state. So typical events are maybe data coming from a sensor, from occupancy sensor, or from a light sensor, or it could be from a switch, a user just pressing the switch to turn on off, or to dim down, or or to change the tunable white label. It could also come from user control, from the mobile app or from the web portal. Events also could come. Or it could be a time trigger based from a schedule, because we also have schedules running on the gateway or on the mobile app. So it's not it can be a bit more complicated because there are multiple factors in play here. Yeah, and the real life state machine is much more complicated than this, and we have multiple of them running on these small edge devices. Okay, so coming to the challenges. Yeah, so system defects. In lighting systems, in general, users have a very low tolerance for defects. And this is a very competitive market. So quality and cost are very critical. If there are any defects on the lighting system, that sometimes can create a safety risk, or it could even have legal or regulatory consequences. Right? So to avoid or to prevent the occurrence of such defects, we do or we apply rigorous testing and validation of the state machines, both on simulations, using simulations, or even on target devices on large scale as well. But in real life, most of the defects are not coming from flaws in the finite state machine design itself. So from the last couple of years, we had a couple of system defects reported from the field, but mostly it's because of abnormal events, unexpected abnormal events. So these events could be caused by environmental variability, because this is a wireless network, right? So depending on the installation site, we may have environmental variations, such as congestion, or it could be interference, or it could be crosstalk. And then because of that, data from a sensor could be missed, or the corrupted data could be received. Other source of defects, it could be also a defective sensor, a defective light occupancy sensor, which happens maybe rarely, randomly, right? So it could be, so one real life case we had was, there was a case where there was a very micro crack in the lens of a peer sensor, which was giving some unreliable data from the peer sensor. So these kind of issues are very, very difficult to find during development or even during factory testing. Even after production, everything seems okay. After installation, everything seems okay. But during operation, rarely we will find those kind of issues. So you may have, as shown in this picture, maybe a building, it's night. You don't expect lights to be on certain floors, but you may get this kind of issues, which is very costly to troubleshoot and then to find these issues. Yeah. So other examples of also abnormal behavior. Yeah, false trigger. Let's say light switching on without actual occupancy. Light artifacts. Light artifacts are some small flickers, on and off lights that happen shortly. Missed occupancy detection. So light does not switch on when someone walks in. So this could be a safety risk if this happens at night. Let's say when, we have multiple examples of those kind of abnormal scenarios. Yeah. So how do we normally deal with this kind of issues? So the classical approach is, of course, we use a lot of signal processing algorithms, and we try to develop the firmware as robust as possible. So we implement we try to handle all corner case scenarios. We have exception handling. We implement graceful recovery. We implement keep alive mechanisms, and so on. So these fundamentals still remain essential. We still have to do that, right? But there is a natural limitation to such rule-based logic, right? Because rule-based logic works very well for scenarios with expected behavior, right? So expected patterns. So, but anomalies are rare. They are unknown. They are unexpected. So we cannot be prepared. We cannot have a firmware which is prepared to handle those kind of anomaly situations, right? So now we are thinking, okay, could Edge AI help us to deal with such kind of anomalies? Yeah, can we embed some AI models into our devices where we are able to detect basically such kind of issues when they occur? Right? So why we think it will be feasible? One, there will be no remote data logging needed, because as you know, ZigBee is a very low bandwidth protocol, so we cannot log too much data. So the failure patterns are quite dynamic. They change over time, they change over environment, so this will also be a good topic for Edge AI. Decisions depend on mainly interacting signals. There is sensors, there is timing, there is the network behavior, there is context, what the user is doing at that moment. So there is a lot of dynamic behavior there. Yeah, so these are the reasons why we think Edge AI could help us, and some application areas where we think we can use it are, for example, sensor faults. So that the peer sensor, which I just mentioned earlier, which from outside look, it looks like everything is okay. There is already data coming from the sensor, but if you have a closer look at the raw data, there are some unreliability there, right? So those kind of anomalies could be potentially be detected using some models. Flicker patterns and abnormal switching behavior. This also we had in real life, when there is some kind of noise on the mains line itself, this kind of flickering will happen. So it took us quite some time to figure out, the problem was not the sensor itself, but it was some noise coming from the mains line itself. Communication abnormalities on the ZigBee network itself. That's also another area where we believe you can use it. Just to give you one application use case which we have already done, this was a master's graduation project which we did at Signify. I also see Tanir in this symposium. Yeah, I did it also with Tanir. So the goal of this project was, can we develop a model to detect and classify some wireless ZigBee network issues. So things like congestion, wireless interference, or blockage. Let's say if you have a luminaire which is positioned at some corner blocked by some concrete wall, basically it is blocked, right? So it can transmit well, no problem, but it cannot receive, right? It cannot receive well. So those kind of issues we wanted to identify. The input to the model was a set of parameters coming from ZigBee diagnostic cluster. We call it ZigBee diagnostic cluster. So ZigBee, that cluster provides us a number of statistics, basically counters at different layer, at MAC layer, at network layer, at application layer. So we have data such as, the number of received broadcasts, number of missed unicasts, and so on. So we have those statistics, and then we try to develop a model basically to be able to classify the possible issue. So the results were positive, but we used basically fault emulation basically to generate the data. So we have not yet extensively tested this in real life. And the main reason also for that is this approach was designed not for edge inference, but it was for offline inference. So data has to be collected from the devices, and then we have to do this in the cloud or on the PC. But the problem already is we have very low ZigBee bandwidths. So we cannot collect this data and then push it to the cloud for offline analysis. The main reason also for that, why we couldn't do it on the edge, was at that moment our devices didn't have enough computational resources to do it on the edge. But recently we have moved to a new microcontroller from Silicon Labs. So this microcontroller has an onboard AI ML hardware accelerator. It also has a slightly bigger internal flash, so we get up 50% more internal flash to store ML models. So now we see an opportunity to deploy the model on this target device. Yeah. Yeah. So we are also currently working with some students, basically to develop a workflow to look into how can we target models which are already done on the PC for the target device. So Silica Labs comes with an SDK. In the Silica Labs SDK comes with a profiler, AI ML profiler. This profiler, we can run it on a target, or we can also run it on a simulator, basically, and it will help us estimate the expected resource usage for that specific model. So how much flash memory we may need, how much RAM, and also in terms of CPU load. Yeah. So this is one example. For example, one model which we profiled. What you can, so this side is without an accelerator, this one is with the accelerator. So what you can already see is by using the accelerator, we were able to see a 10 times better inference time. So we can go from 1.5 inference per second to 15.1. So by the help of the accelerator, we see some opportunity, right, to realize this on the device. My last slide is about this, so open topic. So still, the design space exploration remains an open challenge for us. So what that means is, what is the most efficient workflow to develop models for on-device inference while balancing accuracy, memory usage, and compute load? Most model training is, for most companies, these days, they outsource the model training to a specialized partner company because they may not have the expertise at home, in-house. Then the development is inherently iterative. So you have that hyperparameter selection, model training, validation on target. Then you need to do resource profiling on the actual hardware, including inference latency. But then there should be a loopback based on these findings, right? So there should be a tight feedback loop between the training team and the product team to converge to a certain solution. And then that workflow still a challenge, yeah, to work with. Yeah, that's all what I have. If you have some questions, I'm happy to answer.
Questions?
Yeah, thank you. You mentioned the use of classical signal processing previously. So to what extent do you still use classical signal processing? Do you reinvent the wheel using just AI, or just you combine both together?
For most of our sensors, we still use signal processing. Data coming from a motion sensor, from a mic, or from a light sensor, because there is a lot of predictability there. So whenever there is predictability, we prefer to use signal processing. It's still giving us very high accuracy. So accuracy of, let's say, our algorithm from a pure motion sensor is very high. So we only allow one false trigger per 8,000 hours. So that is a 99.99 something accuracy level. Yeah, doing those kind of algorithms, we still prefer to do it with the signal processing algorithms because it is already giving us the accuracy we are looking for. Yeah.
Any other questions? What about data sets? Do you have data sets?
We
collect your own data sets?
We have plenty of data. We have plenty of data because, as you saw in the IoT system, every luminaire has an integrated sensor. So from those sensors, we are collecting huge amount of data on motion, temperature, humidity, occupancy, the Zigbee network itself, the user behavior, how a user uses also the light. So we have some beyond lighting applications we are trying to build based on that data. But then that's for things like space management or indoor navigation and things like that. We use them, but they are all cloud-based applications. They are not intended for edge. Edge. Yeah.
Okay.
Okay.
Thank you
All right.
very much.
Thank you.